Welcome to another explainer. Have you ever looked at advanced physics and just felt, well, completely intimidated? You're definitely not alone. Today, we're going to crack the code of simple harmonic motion and rotational dynamics. And honestly, the best part? We're going to do it by taking a trip right back to your childhood. We'll use simple playground analogies to decode concepts that usually leave college students scratching their heads. If you've ever opened a physics textbook, taken one look at all the calculus and trigonometry, and felt a cold sweat coming on, I want you to take a deep breath. Does physics math look like an alien language to you? It kinda does, right? But I promise you, it's so much simpler than it looks. We really just need the right translation guide. Welcome to the physics playground. Think about it. Swings, bungee springs, merry-go-rounds, they're all perfect, real-world examples of the exact formulas that seem so terrifying on paper. When you actually understand how a kid on a swing moves, you literally hold the secrets to the mathematical patterns that run the universe. We're going to take those complex symbols and translate them right into simple child's play. Okay, here's our game plan for today. 1. The physics playground. 2. Springs, bounces, and energy. 3. Swings and small angles. 4. Merry-go-rounds and torque. 5. Our final exam review blueprint. And 6. A pop quiz challenge. Section 1. The physics playground, where forces and motion become child's play. Let's get right into it. Okay, let's dive into the absolute most basic rule of our playground, the rule that governs everything that bounces or jiggles. Think of equilibrium as a spring's favorite resting spot. If you pull a block down or push it up, the spring applies what we call a restoring force. It's exactly like a little kid who wanders away from their parents at the park. There's immediately this invisible force pulling them desperately back to their safe spot. Mathematically, it's just F equals negative K times X. And that negative sign? It literally just means that the force always points back home. Section 2. Springs, bounces, and energy. Turning differential equations into simple puzzles. Now, let's see how this builds into something that usually terrifies students: differential equations. If you're panicking at the complex equation you're seeing, stop right now. Seriously, this is not a complex math problem. It's literally just a game of match the shape. We have a standard template for simple harmonic motion, and our only job is to make this terrifying-looking equation match our nice, simple template. Here's exactly how we play the game, step by step. Step 1, we want that derivative part to sit all by itself, so we just divide the whole equation by 4. Step 2, we match the shape. In our golden rule template, the number sitting next to the x is always angular frequency squared, or omega squared. So it looks like omega squared is sitting right there in the 25 chair. Step 3, simply take the square root of 25. Omega equals 5 radians per second. Boom! See? It was just a matching game the whole time. No way you're failing this now. This brings us to a brilliant way to look at energy in our playground. Think of potential and kinetic energy as 2 buckets of water sitting on opposite sides of a seesaw. When the spring is stretched all the way out, at its absolute maximum amplitude, the potential energy bucket is super high in the air, full to the brim. But because the block has stopped moving for a split second, the kinetic energy bucket is totally empty. As it snaps back toward the middle, the seesaw tips. Potential drops, kinetic rises. The total amount of water never ever changes. It just sloshes perfectly back and forth. Section 3. Swings and small angles. The secret rules of the simple pendulum. Now that we've totally mastered the bungee spring, let's walk on over to the swing set. A big question that always pops up is why the angular amplitude of a simple pendulum has to stay within 4 degrees. Well, for all of our beautiful, simple math to work, the swing actually has a speed limit. Actually, scratch that. It's more like a height limit. If you swing too high, the path curves way too much, and the math gets insanely complicated. But if you keep the swing small, under 4 degrees, the arc is so incredibly flat, it basically looks like a straight line. This lets us say the tangent of an angle is roughly equal to its sine, which is roughly equal to just the angle itself. It's a total physics cheat code that lets us treat a swinging pendulum almost exactly like a bouncing spring. Section 4, merry-go-rounds and torque, upgrading from linear pushes to rotational twists. To make this jump, we just need to translate physics speak into kids speak. In standard linear motion, we have Newton's famous law, right? Force equals mass times acceleration, F equals m. You can just think of force as a straight push, but on a merry-go-round, you don't push straight, you push in a circle to make it spin. So in rotational motion, we replace force with torque, symbolized by the Greek letter tau. Torque isn't a push, it's a twist. Just like we swapped force for torque, we gotta swap out the other letters too. Instead of mass, the m, we use I, which stands for moment of inertia. Think of moment of inertia as just the bulkiness of the merry-go-round. Basically, how hard is it to get this thing spinning? And instead of linear acceleration, A, we use angular acceleration, alpha, which is really just the spin-up speed. So F equals ma simply becomes torque equals moment of inertia times angular acceleration. Push becomes twist, mass becomes bulkiness. It's the exact same logic, just spinning around.
Section 5, Final Exam Review Blueprint, your ultimate cheat sheet for simple harmonic motion.
We have covered a ton of ground, so let's synthesize all this into something you can actually use. Here is everything we've learned all in one handy place. The bungee spring is simple harmonic motion. Its equation tells us it always wants to bounce back to the middle. The swing set is the simple pendulum. And the incredible takeaway here, the letter M for mass is nowhere in that formula. The time it takes a kid to swing back and forth depends only on the length of the chain, not how heavy the kid is. Mind-blowing, right? And finally, the merry-go-round is rotational dynamics. Twistiness equals bulkiness times spin-up speed. Memorize these simple translations and you are absolutely going to dominate your exam.
Section 6, Pop Quiz Challenge, testing our new playground logic.
All right, it is time to put your brand new decoder ring to the test. I'm going to throw some real exam questions your way, and we're going to solve them using nothing but our playground logic. Ready? Question number 1. Think back to our energy seesaw. At what exact displacement, meaning how far from the middle resting spot, will a bouncing spring's potential energy and kinetic energy be exactly, perfectly the same? To solve this, we literally just set the two buckets of water equal to each other. Kinetic energy equals potential energy. Because the 1/2 K is sitting on both sides of the equation, we can just cross it right out. Do a tiny bit of basic algebra to solve for x, and you get amplitude over the square root of 2. That right there is the exact mathematical spot where the seesaw is perfectly balanced. So the really crucial point here is noticing the pattern we just used. Almost every physics word problem follows a foolproof 3-step pattern. Step 1, what did the ride give us? In that last problem, the given was that PE equals KE. Step 2, what's our magic decoder ring? We pulled out our specific formulas for kinetic and potential energy. Step 3, plug it in and turn the crank. You just do the basic algebra to solve for x. Let's try this 3-step pattern on something a little trickier. Question 2, we are back at the swing set. If the time period of a swing's oscillation is magically doubled, meaning it takes exactly twice as long to swing back and forth, what is the percentage change of its effective chain length?
Okay, step 1, what's the given? The new time is double the old time. Step 2, decoder ring. We use our trusty swing set formula. Step 3, turn the crank. We set up a simple ratio for the new time over the old time. Since the time is doubled, the math clearly tells us the new chain length must be 4 times as long. To find the percentage change, we take the new length minus the old length, divide by the old length, multiply by 100, and wow, you get a massive 300% increase in length. See how easy that pattern makes it?
Final quiz question, let's bring it home. We have a tiny little merry-go-round slowing down from 120 rotations per minute to a dead stop in 30 seconds. What is the applied torque? Using our 3 steps again, first we find the spin up, or in this case spin down speed, alpha. Then we find the bulkiness, I, based on the mass and radius. Finally, twistiness equals bulkiness times spin-up speed. Multiply them together and we get a twisting force of exactly 0.1047 Newton meters. Look at that! You just crushed a high-level rotational dynamics problem. And there you have it. We took some of the absolute scariest equations in physics and completely conquer them by simply taking a trip to the park. So next time you walk past a playground, take a look at the swings, the springs, and the spinning rides. Will you just see child's play, or will you see the beautiful, invisible math running the universe, knowing you finally hold the decoder ring? Thanks for joining me on this explainer. Keep learning, and I'll see you next time.